What drives someone to spend decades mastering flight? Not from the cockpit, but from the drawing board. From building model airplanes at age 3 to designing cutting-edge carbon composite aircraft, Dr. Naresh Sharma has spent his life reimagining the way the world flies. Welcome to Industry Ignited, the show where we uncover bold ideas, visionary leaders, and groundbreaking technologies reshaping modern industry. I'm your host, Dr. Leeanne Aguilar. And today I'm joined by Dr. Naresh Sharma, CEO and President of NASHERO, a company pioneering the next generation of advanced aerospace solutions. Naresh, welcome to the show.
Thank you very much for inviting me, Leanne.
You're welcome. I'm looking forward to today's conversation. Now, you've said that your love for airplanes began when you were just 3 years old, peeking through the doors of a hangar. What do you think sparked such an early fascination with flight?
I don't know. I must have had some tick in me at that point in time. But I remember that I had, at that age, never seen a real airplane. But I liked the smell of that hangar, and I related it to something that must have been there in my life, which. So it's a very difficult question to actually give you a substantive answer to. It's more related to how I felt at that point in time.
Yeah, but just peeking through that hangar door, you just, a fascination was sparked is what I'm
I
hearing.
was
Kind of.
totally nuts about
Yeah.
airplanes. And
Uh-huh.
that's why my cousins had taken me over there to the hangar. And there were supposed to be airplanes there and sailplanes. And unfortunately, that thing was closed. So I just had the opportunity to peek through the little crevices which are left between the hangar doors, which are really large, and the wall that supports it.
Yeah. And you got to see a real airplane, and that's
Yeah,
how it started.
yeah.
Now, you grew up on the IIT Camper campus, surrounded by incredible engineering minds. How did that environment shape your curiosity and future ambitions?
So this is a very good question. Actually, being at the IIT Kanpur campus was a real privilege for me. Because not all Indians had that opportunity to be living in a campus which is full of technology, innovation, and the best minds that were there at that point in time. And that indeed, if there was a question in my mind, I just had to make a simple effort to go to some of the friends of my father's and ask them why does this happen, how does this happen, and they were all open to answering anything that was in my mind, and that was a huge boon to me.
Yeah, just having that access to people who are living and breathing and working at the forefront of technology and in that space.
I was so crazy about this. I'll tell you one thing, that when I was 5 years old, I was in my first grade. And there was a gentleman called Dr. V. Adimurthy. He had just got his PhD from IIT Kanpur in mathematics. And his first job, and I would tell you that he retired from that job from the same place, was at Indian Space Research Organization, ISRO, that sent the rover to Mars, and they landed on the other side of moon very recently at a shoestring budget. So I was so crazy about planes and anything that flew, that when Dr. V. Adimurthy came to our class to give a talk about what he was planning on doing after his PhD in mathematics, at 1 year old, I remember I had an autograph book, which had autographs of some of the top people, politicians, president and prime minister and all that. I had him autograph that autograph book.
Really?
Yeah.
Yeah. So you just could see his potential and see that he was someone who was going to make big things happen in the
Right.
world. And you were just fascinated also. I mean, you saw him as a hero at that
Right. For
young
me, technologists have been always the people who I have felt closest to, because they create the world in which we live.
Yes.
Politicians do not.
Yeah. Well, and that makes sense. I mean, they create things that really impact the way we live, advance technology, advance knowledge. And so, right, we that actually impact day-to-day life. That makes sense. Now, your path from mechanical engineering to aerospace was a bold move, especially against your father's wishes. What made you take that leap?
So, like I mentioned to you twice, I was nuts about airplanes, and my father was not very enamored by them because he went for his training to MIT through the government of India and government of US, some bilateral relationship, due to which IIT Kanpur was also set up. He had seen some of his friends sort of getting out of the job after the Apollo programs. Apollo programs were closed in early 70s, and he didn't want his son to be part of that group. So he was very adamant that I should not do aerospace engineering. But after working for a year as a mechanical engineer, I resigned from my job and went back to IIT Kanpur to do a master's in aerospace engineering. And yeah, that was I'd crossed the red line for him by then. So
Yeah. Did he ultimately come around, or was it still?
I think um, I think my father was a very complicated person. Means he wouldn't take no for an answer. So even when the airplane that I designed in India became a grand success, he never acknowledged that. When I came to Delft, also he never acknowledged that. He said you should stay in India and help Indians excel. And I told him I want to excel in technology. Technology doesn't have any boundaries.
Right.
It doesn't have any nationality.
So looking back, how did those early experiences, even the challenges, like you mentioned, influence your leadership style today?
Well, like I said, I believe that technology is something that I really enjoy and love. And it has got nothing to do with whether it's aerospace or it is computer sciences or it is AI. And I dig into it, into all of these aspects with as much effort as I can muster. So, when you talk about the relationships that I have had and the development that I have done till now, every little bit of fundamentals that you learn in your undergraduate and also in graduate school, they play a huge role into how good of an engineer you are and how broad based of an engineer you are. Because being, for instance, people say that you have a PhD in aerospace engineering and computer sciences, but that's not what a PhD is. PhD is a process that you learn about how to dig deep inside into a problem and get the answers which do not exist. So
Right.
it's understanding of a process. And that understanding of a process you learn whether you apply it to a certain aspect of your current problem or you apply it to a different aspect of your problem, it's up to you.
Hmm.
So um, all the issues that I look at them fundamentally, and that is what is appreciated by the students who are over here. For instance, we had a student on who worked on Hamiltonian mechanics, which is a very different thing from composite materials. Another student who worked on flutter and aeroelastic behavior of aircraft, which is also a very different thing than actual aircraft design. And that happens because of the way I look at technology. I look at it more fundamentally than an applied aspect of technology. I hope that
Right.
answers what you asked me.
Yeah, yeah, I think so. I mean, it's like you're right. I mean, when you go through school, you're learning principles, you're learning how to learn, and especially through a PhD program, it's learning how to research. You're getting into what previous people did in the past to, I mean, how you got to where you are now. But the whole point from that point is to expand knowledge. I mean, from there, you're tasked to go out into the world and discover things or learn things or create knowledge that doesn't exist before. That is the whole, what PhDs are tasked with. And so whether or not someone is in that exact or what they studied in their PhD program isn't exact alignment or not with what you're developing technology wise doesn't really matter, is what I'm hearing, because they understand the fundamentals of how to expand knowledge and how to research and what to look for. And so having that base of knowledge creates that or possibility.
Basically, I'll make a similitude of what is a PhD. PhD is like it gives you the tools. It gives you a drilling rig. Where you drill and how deep you go depends on the need that you have at that point in time. But the drilling rig is the PhD that you have.
Yeah, it equips you with the tools, with the skill set for going and digging deeper. And where you dig, like you said, and how deep you dig is up to you. So you've been at the forefront of innovation for decades, from designing aircraft in India to collaborating with world-renowned experts like the Professor Stephen W. Tsai at Stanford. What have been the defining breakthroughs along that journey?
I've worked with two real stalwarts of technology. One was Professor Egbert Torenbeek, who actually invited me to Netherlands, and the other is Professor Stefan Tsai. Professor Tsai has been gigantic figure in the field of composite materials. He did the first multi-modal failure criteria for composite materials, because composite materials are very complex. As you know, if you're talking about a metal is isotropic. It has the same properties across each axis, so to say. So it's a very simple thing to calculate for metals. Metal behavior, its strength, its life, a safe life, and whatnot can be done much more easily compared to composites. So in composites, you have a 6 by 6 tensor, which you have to deal with. And Professor Tsai came out with this complex failure criteria, which is on his name. It is called the Tsai-Wu criteria. Almost all the finite element software, they have the Tsai-Wu criteria as a standard criteria for you to be able to figure out the strength of composite material. Having had the opportunity to work with him was also a huge advantage and a huge boon. And I'm truly grateful to Professor Tsai for giving me that opportunity. So the technologies that we have developed with this, Professor Tsai discovered that composite materials have been there for over 70 years. The first
Right.
composite, um, the first composite is a wood. Is a piece of wood, because wood has directional properties. It has fibers in one direction. What Professor Tsai figured out was that in that tensor, in that 6 by 6 tensor that constitutes the behavior of composites in their elastic properties, in that tensor, there is an invariant. And that invariant doesn't change how the angles of plies in a composite material change. And that invariant is actually the trace of the matrix, of that 6 by 6 matrix. And this is a huge discovery, because you can imagine that there have been thousands of composite researchers who have worked on, multiple decades on this, and nobody ever figured out that there was this trace of that, of the elasticity of that stress tensor that is an invariant. This discovery of Professor Tsai is a very, very big discovery, because that allows you to reduce all the stiffness properties of a composite laminate, which has actually been made, into a single variable, which is the trace of that matrix. So this thing is so powerful that it allows you to optimize materials, number one, which was not possible earlier. It allows you to simplify the calculations that you do in order to look at the behavior of a material. And it allows you to create a differentiation between which material is stronger and which material is better for your certain application. And it does a lot of things. So I wrote a paper in 2019, which was to name this trace of the stiffness matrix, to call it size modulus. And this paper was co-signed by almost 27 of his co-researchers over the years, and also people who were not his co-researchers, but people from the composites material business. That thing has made us get a lot of visibility, and that allowed the development of something which is called as the double laminates.
Mm-hmm.
And the double laminates is the only technology in the world today that has the capability of having the structural mass of already optimized carbon composite material. So, carbon composite material, I'll give you an example. Take the Boeing 787, for instance. It has an enormously large percentage of carbon composites in it. So the wing is carbon composites, the fuselage is carbon composites, the
Right.
tail feathers are carbon composites. Now, those are very highly optimized because you don't put even a single ounce of material more than what is required to sustain the strength of that component, right?
Mm-hmm.
So, in an already optimized material, we can reduce using the double technology. We can make that structural mass half.
Wow.
So you can imagine that with it's such a powerful technology, double technology. That is what we're trying to bring to bear in the market. Other thing that is very important that has come as a result of collaboration with Professor Tsai is that I realized that the biggest problem in composite materials is the variability in components. So even Boeing has the same issue, Airbus has the same issue, and the variability comes from one on Monday a part is made and on Tuesday another part is made. They will have different stiffnesses. Their stiffnesses will vary, their strengths will vary, and all that,
Mm-hmm.
even though the material is exactly the same.
Really?
Yeah. So this is called production variability.
Oh, okay. Yeah.
And because of this, we do statistical testing.
Mm-hmm.
So we do statistical testing to look at that, and we create a viable curve. And at the lower end of the curve is the place where we set up the strength of that component so that it is beyond the statistical variance of the material variability that comes as process variability. So we have a process which is a proprietary process of my company NASHERO, which is called the zero void technology that eliminates all the voids in the carbon composite or glass composite or whichever composite material is there. Once you eliminate the voids, you get rid of the localized stress risers in a material. And those, if you do not have stress risers, you have infinite fatigue life.
Mm-hmm. Wow.
So those are the two innovations which I would like to attribute to my being part of Professor Tsai's research group.
Yeah. So as you mentioned that NASHERO is, you have a proprietary composite material that you developed and now it's really rivaling major aerospace players because of its, I guess, the lower mass is what you're saying, and just the strength that it provides as well. And not only that, more consistency in the material. There's not the variability that other composite materials have.
Right.
Yeah.
Exactly. So the variability aspect, human variability aspect, has been production variability aspect is eliminated from it.
Yeah. Now, aerospace is known, though, for its high barriers to entry. How did you build credibility and earn certifications like the AS 9001D and the NATO NCAGE as an independent manufacturer?
So that's always a tough challenge. That's a very good question that you asked. We didn't talk about this in the initial conversation that you had. So let me go back to this. I don't think that we discussed this when we were talking about this interview. So let me just tell you a couple of things. The first thing is it was next to impossible for me to get anybody to supply us carbon composites for our light aircraft. We
Really?
were willing to pay for it, but we were
Yeah.
not getting aircraft grade material.
Why?
I don't know. I don't know. So it was Professor Tsai who called one of the material suppliers and said that you got to supply to him or to his company material. So
Mm-hmm.
we got that. Then how did we enter into the aerospace world and get certified and all that? That is, in aerospace, certification is everything. If you're not certified, you can make the best aircraft in the world. You won't be able to fly it.
Of
if
course.
if you're not certified, you can make the best looking component, and that component will not fly on any aircraft. The critical thing is whether it meets the requirements and the constraints on which it is designed. And that is a critical aspect. We were lucky that there was a project going on in which that was the first time that we did this. We got an offer to make a component for an amphibious assault vehicle. And that component got us through to the NATO NCAGE as well as through the initial part of AS9100D. And that is the time we started doing the AS9100D certification. And then we got some really good talented people in the company. One of them is an ex-Augusta Westland engineer who helped us in ironing out all the requirements of certification norms for AS9100D. And we got onto that bandwagon. One other thing is that I have been working with ASTM since 2008, developing standards for light aircraft. And I'm one of the committee members for the F-37 committee, which is for the light sport aircraft. Okay. And then subsequently, we had a new committee, which is F-44 for general aviation aircraft. That is from 1 seat to 19 seats.
Okay, yeah.
And also on the systems committee, which is F-39. So I'm on these 3 committees and very active on these 3 committees. So basically, it's doing a rewrite of the Part 23, CFR Part 23, Code of Federal Regulations Part 23 in the US. And in Europe, it is Community Standard CS23. So being part of that also helped.
Mm-hmm. Right. No, but that's huge, right? So the certifications open up the opportunity because, like you said, without those certifications, you can create the best parts in the world, but no one's, best components, no one's going to buy them. They're not going to be flight worthy. So now, how do you balance engineering perfection with business realities like cost, scalability, and market competition?
Well, this is again a very good question because of the automotive nature of machine components, because of the nature of the industry where we are located. We are located in the Motor Valley of Italy, and Motor Valley of Italy is very famous for the Bugatti, the Koenigsegg, Pagani, Lamborghini, and Ferrari. And these kind of cars are talked about over here. And being close to suppliers who supply to Lamborghini, Pagani, and Ferrari, quality has always been a plus point of this space. Over here, they also have very tight tolerances, very high requirements for their components. So that is very well known how you get to those tolerances. But the problem of making revenue stick in these times is very difficult in the space, because when you are a high-end automotive manufacturer, you do have to go just a little bit ahead to get the AS9100D certification if you are a precision manufacturer. And quite a few people have done that. So again, while I was going through the AS9100D certification for my company here, at that time I was invited by the cluster of Bologna, which is actually the heart of this Motor Valley, to participate in that cluster as a company in that cluster. So we joined that cluster, which is it's called Innovation and Research for Industry, IR4I.IT. You'd find them there. In that, all the 23 companies who are partner companies in that are AS9100D certified. So that sort of helped me in addressing the issue of how to go about and make this a viable business proposition, and not just not just something that would give us a feather in our cap.
Right. Okay. So it's really just proximity. It's in that location, being close to all of these high-end automobile manufacturers who not only have that technology, but you have people in the community and the associations that are nearby that help you.
And also having the attitude, like I mentioned to you, what you learn from doing a PhD, that attitude is never to take no for an answer. So if you know that there is some equipment out in the market that gives you a certain quality, then you should be able to either make it or you should be able to acquire it.
Right. It's just a matter of how, like you said, don't take no for an answer, just being persistent. And so now NASHERO is known for its precision, like entire aircraft structures manufactured in a single operation. Tell me about how you brought that concept to life.
So, aircraft are usually made from aluminum sheets and formers which are riveted together. These are okay for light aircraft, but every rivet and everything which is bolted together in terms of with sheets or already machined components, if they are forward, if they are touching the airflow, and if they are touching the airflow, they will always have a problem with the flow on top of them, because the rivets will dent the material, and those dents will not allow the flow to remain laminar on the body. So I decided that we're not going to make any metal riveted aircraft in this company. And the metal riveted aircraft also have millions of rivets and lots of small components, which makes it very complicated and very expensive to maintain and manufacture. So I decided from get-go to make parts out of composites. So when you make parts out of composites, the master model that you use in order to build it is a real reflection of the design that you have done earlier. And the design that I had done earlier was the design of a natural laminar flow based aircraft, which would have almost 98% natural laminar flow on the wings. Now, what does natural laminar flow do? Natural laminar flow reduces drag.
Right.
And that is very critical. And in our case, the natural laminar flow airfoil has 98% natural laminar flow, but it is designed in a manner in which the nose part of the airfoil is the shape of the cross section of the wing. It is designed such that if you have, mosquitoes or insects which get stuck on it, that when you go in a car, you go very fast, you get bugs on top of the windscreen.
Mm-hmm.
A similar thing happens on aircraft as well. And those things can reduce the quality of the flow on top of the wing. And from a natural laminar flow wing, it can make the wing a dirty wing. So long as, in our case, the bugs come on the nose, because they usually come on the place where there is an attraction for them to go and hit that.
Okay.
So if the bugs are there for a single flight, they will destroy the flow very low, in a manner which is very local to that area, but then the flow will reattach. This kind of a natural laminar flow wing is not there I don't think that there's any aircraft out there in the light aircraft category that has something like this. And
Okay.
we'll be bringing that out. So that, firstly, doesn't have any rivets. It doesn't have any bolts which are protruding out in the flow. And secondly, it has a shape which is natural laminar flow. So those are the two things which allow us to have aircraft which has extremely high performance.
All
And
right.
then we have got to prove it with the aircraft out. We have to still show our customers that it indeed does that, and
Yeah.
how they'll have to take care of it.
Okay. So tell me about because you have, is it 2 aircraft that are currently in production?
Yeah, so
Uh,
there are two aircraft. There are two light sport aircraft which are under development. One of
mhm.
them is Augusta, which is a high wing carbon composite airplane, and one is a low wing mainly glass aircraft, which is meant for air work. And then we have a single seat sailplane, and we have two larger aircraft. One is 5 seat and one is a 19 seat. These are in our plans.
Okay, those are in plans. But you have two in development, so far. Very exciting. And so your concept of the aircraft without the rivets, is that applicable to larger commercial airplanes as well?
Absolutely.
Uh-huh.
Absolutely. So there is a organization which is called CMH 17, which is Composites Materials Handbook 17. They believe that the aircraft should be bolted together,
Mm-hmm.
whether they are composites or they are metal. I think they have to rethink their thought process, because it is not necessary to have aircraft bolted together. They can be bonded together and have the same strength.
And have the same strength. Okay.
Yeah, and I'll give you an example. The aircraft called the Fokker 100, which was a 98-seat aircraft, and the Fokker 70, which was a 70-seat aircraft, and the Fokker 28, which was also a large business jet.
Mm-hmm.
All these aircraft were metal, but internally they didn't have any rivets. The metal main spar was bonded to the skin, and they had natural laminar flow for a certain extent.
Okay.
And this really lowers the fuel consumption. It increases the quality of the aircraft, because a natural laminar flow aircraft obviously is far more slipperier in air compared to a aircraft in which they are protruding rivets.
Right.
And I think that the CMH17 folks and the others who work with them have to realize that they can't continue talking about putting rivets on an aircraft. So the moment you take a composite aircraft and it has layered fibers in this, and you pop a hole inside it, you are reducing the strength by a significant amount.
Right.
So all the advantage that you get by having the bias of fibers in a certain direction is lost if you drill a hole inside it.
Okay.
So, like I said, never take no for an answer. We'll keep working on it, and we'll prove it to them on a smaller size, smaller scaled aircraft that it works. And then it's up to the people to realize and put it in practice on larger aircraft.
Right. And I think that's often what it takes. It's just that one proof of concept that says, see, it does work. And then, right, it opens up the possibilities, at a larger scale. Now, what role does automation and AI play in your manufacturing process? And how do you see technology continuing to shape the future of aerospace?
So that's again a very good question. AI is going to be a game changer in our business. In our case, most of the automation that we have in our facility is done using AI. We have internal servers. We do not take our data outside and use AI tools which are online. We have everything installed internally. There are fortunately some tools which are very good, like the large language models from Olama. Olama is a platform which integrates quite a few tools inside it. And we use those tools. We use automation systems like N8N, which allows agentic automation. And it allows you to develop RAG is retrieval augmented generation based tools. And those two things combined together with a nice database system allows us to control everything that is there in our facility to the best capability that anybody can have. So that is one aspect in which we are using AI right now. What we want to use AI in the future is also for our AS9100D customers. We haven't done that yet because they haven't asked for it. But yeah, we can make this happen. That is, they would be able to use AI tools to get insight and access into our ERP system and track the progress of their jobs that we are running on our machines, for instance.
Interesting. Okay.
Yeah. And we can also, all the management of things, warehouse management of materials, management of machines. These things are very easily done by AI. So we use as a means to allow us to do things which would have required several people to do those things.
Right. So it creates a lot more efficiency, and also
It
opens
doesn't
up.
require the problem of interfacing between various areas where, for instance, you look at aerodynamics and you look at structures, and you want to exchange data between them. You would need somebody who understands both.
Yeah. Now, you've mentioned plans to expand into the U.S. with potential locations in several states. What factors are driving that move?
Okay, so the biggest driver is, I think that in the world, US is the only country which understands aviation really. There is no other country out there which understands and implements aviation as a tool to develop its own business, workforce, power, and the society. You might be surprised to know that if there is an airport in a small place, that increases the access of the people who are living over there, and it brings in access from the other areas in that area, in that location. This kind of a thing is not there in other countries. So
Okay, interesting.
this was the main reason.
Mm-hmm.
And then there was a significant and aggressive interest from several states in the US who wanted to have the technology that we have locally in the US.
Yeah.
So this helped us look at what is the best way forward for the company. And most of our investors in NASHERO are Americans already. So that was a no-brainer to consider that US would be the top priority for us as far as setting up the growth part of our company is concerned.
Okay, so that would be like a larger scale manufacturing facility that you would,
Right.
that
And the need is also there. In the US, the
Mhm.
need is there. US currently it lacks large scale manufacturing capability. And with automation and the way in which we do things, we would be able to bring to bear capability that US really lacks today.
So what is your long-term vision for NASHERO, both as a company and as a legacy in aerospace innovation?
So I would say that it would be pretty bold for me to say that, but NASHERO wants to be the top manufacturer in the world of light aircraft.
An aircraft. Got to have vision. That's where it starts, right? Now you've lived and worked across continents, India and the Netherlands and soon the US. How have these global experiences influenced your approach to innovation and leadership?
It's given me a much broader perspective as to how various people think of technology, how they value technology, how they value the innovation. Means we have 75 innovations in our aircraft itself, aircraft and production processes. Not all countries view them in the same way as some other countries. And availability of funds and the risk-taking nature of people among investors, that is different in Europe, it is different in the US, and it is different in India. Then availability and maturity of the market itself is very important, because in aviation you cannot make something and then hope that the political system will change and the political system will enable you to make that thing that you have created succeed. And this is my this is the nemesis of the developing world, so to say,
Right.
because they have the capability, but there's a delta between what the political system allows them to do and what their capabilities are and what would make them internationally competitive. So, taking everything into mind, you require that kind of experience to have worked in on both the sides of the pond, as well as looked at how various countries work and behave.
That must be frustrating, right? It's like having the technology, having the resources and the capabilities, like you said, but then there's the political policies or whatever that are holding you back, regulations, and so it's deciding where to take the innovation in order to make it possible, and right. And then some countries are slower to develop or to allow things than others. And so I guess you do
So
have to be strategic. Yeah.
I'll tell you, I'm not the only person. Fokker, Anthony Fokker, who actually created the Fokker Aircraft Company, he ran around in circles before he could build an aircraft company. He built all his aircraft companies in Germany. And then later on, because nobody in Netherlands would want to trust him into building aircraft company, he flew a plane in Haarlem, showing the plane up on top of the Tower of Haarlem, and nobody took him seriously. So that's deja vu that all innovators see. So today, some fellow will come up with a large language model or a new technology in order to, that large language models are not only built using transformer technology. So suppose somebody comes up with a new technology which is not transformer based, people laugh at him, for now at least.
Right. Well, that's history, though. I mean, looking back at innovators throughout history, they get laughed at and until they and it's not always in their lifetime, which is sad, right? It's like sometimes their ideas and their technologies don't get proven until generations later, oftentimes, and then it's like did work after all. that is frustrating. Now, the aerospace industry is facing pressure to become more sustainable. How does NASHERO's work with advanced composites contribute to that mission?
So, like I told you, with Professor Tsai, in which I've co-authored 3 books with him, I have chapters in 3 of his books. In the last book, we have written about how the DD technology implemented in the current aircraft. So suppose we take the 787 example again, and the 777 example, or the Airbus 340, 350, and the 380. These are large jets from Airbus. Suppose these were built from composites. You would have already saved 32% of
Fuel.
greenhouse emissions.
Yeah, absolutely.
And you know that for 1 or 2% increase of enhancement of performance of the large engines like the Trent, government put in billions of dollars, billions of pounds. The billions of pounds went into the Trent program from the Horizon program of European Union. So, and we are talking about 32%.
Wow. That's huge. Very significant.
Yeah.
Yes.
So every passenger, so the basic advantage is that you'll be able to go further with the same aircraft because you'll be able to carry more fuel.
Right.
Or you'll be able to carry more passengers with less fuel.
True. Yeah. Game changers for sure. Right. Now, what advice would you give to young engineers or innovators who dream of changing the world through technology?
I would tell them that don't stop at the first thing that excites you. And you dig as deep as you can. Your education only gives you those tools. Like I told you, they give you the big drill. And if you have a PhD, your drilling rig is perhaps slightly bigger with a vaster set of tools.
Sure.
If you have a bachelor's, maybe you have a small drilling rig, but all of you have a drilling rig. But that doesn't mean that with a smaller drilling rig, you can't get to diamonds. And with a larger drilling rig, you'll always succeed in getting oil.
Yeah.
So
True.
it's a complex thing. There's an element of luck, but you should not stop at the first thing that you get to. And you should continue your search and stay curious and read a lot. Because the more you know about what other people are working on, the more you'll be able to think about how you should behave and what you should do.
More tools in that, on that rig, right? More tools in the belt. The more you educate yourself, the more you learn from other people, and then take that and build upon it. So you're not starting from scratch all over again and reinventing the wheel. Exactly.
Right. And follow your passion. Follow your passion. If it is your passion to do something, then you follow that passion.
Yeah. And finally, Naresh, if you could go back to that 3-year-old boy peering into that hangar, what would you tell him now?
I was already I was very motivated then. That's a very tough question to talk about somebody who is already motivated. I would say that try to think about how can you convince your parents if there is somebody who's has more control over you. In India, at least, it used to be
Uh-huh.
the parents.
Uh-huh.
And when you're grown, then maybe it would be your partner, it would be your husband, it would be your wife. And when you have children, it could be your children. So basically, convince whoever is around you to bring them along the journey, because this journey will not only change your life, it will change the life of people who are around you, and most often for the better.
Yeah. But that's the challenge, right? Getting other people to see your vision, getting other people to come along. It's not always it's easier said than done, right?
Yeah, yeah, it is.
Now, Naresh, your story is a testament to what happens when relentless curiosity meets disciplined innovation. Thank you. I really appreciate your sharing your journey and for giving us a glimpse into how NASHERO is shaping the future of flight. For listeners who want to learn more about NASHERO and your groundbreaking work, where can they find out more?
They can go to our website, which is www.nashero.com or www.nashero.it. They can connect with me on LinkedIn and go on our website and ask for questions over there. And thank you very much for inviting me.
I've enjoyed our conversation. It's fascinating. I know I could probably listen to hours more of the very interesting work in technology that you're up to. And to our audience, if you enjoyed today's conversation, don't forget to subscribe, share, and join us for the next episode of Industry Ignited. Until next time, stay bold, stay curious, and keep igniting industry.